Hi, I'm Ahmad Milad, and I'm really excited to share our project, location and orientation detection of LEGO Shuttle assembly. This has been a team effort, and I'm fortunate to have worked with my talented teammates, Pallav Kamojjhala and Elan Wilkinson. Together, we took on the challenge of using computer vision to estimate an object's orientation in 3D space. Our system combines YOLO for real-time object detection and Resonant for accurate rotation prediction. This approach has incredible potential in fields like robotics, industrial automation, and more. By blending these cutting-edge AI techniques, we were able to bridge the gap between virtual models and real-world environments. So now let's take a closer look at how we brought this idea to life, the challenges we encountered, and the creative solutions we developed along the way.
In industrial, auto manufacture, aerospace, or medical device contexts, verifying a part has been correctly attached to its orientation is of crucial importance. This requires detection and understanding of the orientation of the object in question. If the position of the camera relative to a structure or space is known, the ability to determine if a part is correctly oriented can be used for guided instructions, robotics, or inspections. Assembly parts for industrial or work aid purposes are often proprietary, require approval for use, and can be challenging to source. In order to simulate the complexities of these real world challenges, we designed a simplified experimental scenario as a toy problem using a Lego shuttle parts as proxy for the actual industrial parts relevant to a buildable assembly. What this did is it enabled controlled testing and validation of the pipeline and project methodologies, which are designed to be scalable and adaptable for application to real world industrial parts and assemblies. Our bounding box and classification models were trained predominantly on synthetic data, and our orientation model was trained exclusively on synthetic data. Acquiring sufficient volumes of real world data for parts and structures in industrial environments can be very costly and time consuming. In emulation of the real world constraints on training parts, synthetic data was created and used to train the model. This also allowed for very precise rotation labels when training the model, which was critical for our particular application. Our pipeline for synthetic data generation was fairly straightforward and consisted of rich point cloud capture through Gaussian splatting using the Scaniverse app on an iPhone 13 mini, and then conversion to a mesh. This was then imported into the 3D tool Blender for mesh cleanup, where we removed the captured background during that point cloud generation. It was then finally imported into the Unity tool, which is a real-time 3D visualization and game engine application. And from there, the background table, camera angle, light intensity, light temperature, distance, and camera offset were randomized when generating that data, and annotations were automatically added. For training the YOLO classification and box detection models, videos of a LEGO shuttle were processed to extract every 10th frame, which was rotated and saved as images. Images were then annotated with MakeSense.ai and used for training. For testing orientation data, images were captured at human estimated angles in 45-degree increments and labeled. For further testing, live camera data was used from a webcam for box and rotation detection and further verified and analyzed against expected values. A desktop webcam AR application was created for label data generation and validation, but this particular application requires refinement and adjustment prior to incorporation with the project.
Coming to our two-stage detection, while we were exploring our project, we decided that decoupling the functionality of detecting our object in our frame or our video capture and detecting the rotation of the object would be better if the functionality was split up. So our general workflow would be capturing the live feed, passing it to our object detector, and then the object detector then passes it to our rotation detector. So let's dig into those stages in depth in the next slides.
YOLO was an important aspect of our project for detecting the LEGO shuttle's bounding boxes. We started by capturing video footage of the shuttle in both half and full configurations, using tools like OpenCV. We pre-processed the video frames to get them ready for the training. We also had a custom-made application by Elan, which captured this data and pre-processed it automatically. That was also used in training our YOLO model. The data that was captured from the video was then fed to MakeSense.ai to annotate the frames, creating a structured data set specifically for YOLO. And then we built our model on the pre-trained YOLO v5 weights, which helped speed up training. We set the model to train with a batch size of 16, an image resolution of 640 by 640 pixels, and then we run it through 50 patches. The training patches took time, but it was worth it because it helped with the precision of the model. So for the evaluation, we use metrics like mean average precision at intersection over union of 0.5, which stabilized near 1, showing the model's high accuracy in detecting the shuttle. We also measured precision and recall, both of which were nearly 1, indicating very few false positives and false negatives. The model proved to be robust, consistently detecting the shuttle even in challenging conditions like very lightning, different angles and complex backgrounds, noise in the background, and so on. Its real-time performance not only enables bounding box detection, but also sets the stage for other tasks like estimation of the shuttle's rotation. So with these results, we can now pass the YOLO output to models like Resonant for rotation prediction and Meadows for depth estimation. So this two-step process significantly enhances the overall system's accuracy and then allows us to more effectively estimate the shuttle's orientation in 3D space.
It's here that we enter the second stage of our model architecture, orientation detection. When exploring and evaluating model architectures for orientation detection, pre-trained YOLO and non-pre-trained CNN approaches were explored, but ultimately the use of a residual neural network demonstrated the best performance. Residual connections or skip connections allow data to bypass some layers when flowing through the model and feed directly as inputs to another layer further down, helping to address vanishing gradients. The 18 in ResNet 18 refers to the 18 layers of the model. ResNet 18 and ResNet 50 performed comparably when not freezing weights when training, so the smaller of the two models was kept for speed of training and prediction. When performing hyperparameter tuning, it was found that the optimal performance was achieved with the Atom Optimizer, a learning rate of 0.00001, mean squared error for the loss, and training for 15 epochs. The dataset itself used for training consisted of 20,000 images of synthetic data, with a trained test split of 80-20. The model was evaluated both on a validation set of synthetic data as well as real-world images that were captured. We did see that the model performed slightly better on synthetic data, but due to training exclusively on synthetic data, some overfitting was expected. In looking at our results, we did have the output results converted to Euler degrees for human readable comparison. And as we look at here along the X, Y, and Z axes, the X here essentially corresponds to pitch of the object relative to the camera, the Y to yaw of the object relative to the camera, and Z to roll relative to the camera, although this value should be 0 for all images synthetic and real world. In the synthetic data, we saw a mean average error of 1.2 degrees or 0.3%, 1.9 degrees or about 0.5%, and 0.5 degrees in the z-axis, corresponding to a 0.1% error. In our real-world data, we saw an average pitch error of 9.6 degrees or 2.6% and 17.2 degrees for our yaw or about 4.7% and 1.9 degrees or 0.5% for our roll. With these, we did see that using the median rather than the mean, we saw an error rate of 8.5 degrees and 6.7 degrees for X and Y respectively, reflecting that we do have a few outliers that did drive up that mean average to that 17.2 degrees. As well, it should be considered that the nature of our real-world capture relying on human estimates means there was inherently a small level of error in the reported angles, so these error rates are likely inflated. In future iterations, the use of AR tools could provide more accurate insights, as well as other precise measurement mechanisms.
Now, again, coming to the orientation detection and running the model in real time. As discussed before, we first doing a video capture in real time, so we're using this Python CV2 library to be able to capture the video and analyze each frame. The next step would be to actually detect our object in the environment. So we had two models for that, as discussed. We had YOLO and an RCNN model to recognize and predict bounding boxes. So in each frame, our model would grab the bounding box and be able to crop that frame and pass that to our step 3, which is our rotation detection. So in the rotation detection, it's expecting a closer up image of our object, which we've trained our rotation detection model on. So this aligns with the input format and of the model, and also just it more closely aligns with the type of data that we trained our model on.
So despite its strains, our system faced several limitations and challenges. For example, overfitting to synthetic data led to reduced performance when transitioning to real-world scenarios, as the model struggled to generalize from the control conditions of synthetic data to the variability of real-world inputs. And then manual annotations also introduced small errors that slightly impacted the prediction accuracy. We believe ensuring accurate and consistent labeling is very important for improving model reliability. Additionally, the limited computational resource provided by Google Colab constrained our ability to train larger, more complex models or process larger datasets, which would have enhanced performance and robustness of our models. And then I believe another challenge was capturing a diverse dataset. It presented its own challenges, as we were limited by the amount of video data that could be processed or stored efficiently. And then improved hardware such as high resolution cameras, dedicated GPUs, and more advanced annotation tools could also significantly enhance the data quality and reduce manual errors. Addressing these challenges will be very important for scaling the system and then ensuring its reliability across diverse real-world application will also require tackling these challenges. And then finally, object orientation detection also introduces challenges that are specific to this application. The lack of depth information greatly hampers the precision estimation of the angles, making it difficult to determine the exact rotation. I believe in general, models relying on 2D images struggle with this, as they cannot infer 3D rotation accurately without having information about the depth.
Now let's take a look at how it's actually performing in real time. So for testing it in real time, we took two approaches. So the first one was to have the camera in a stable position above the object. So the camera is stable and we manually rotate the object in different directions to view the angles. So in the first video, the standard, we used like a reference image where we had some ground truth data. And we wanted to test that posture and see what our real time is giving us. And within just a couple of degrees of error, we are able to actually see that our item or our object actually shows the proper angles based on the testing data posture. So with our Z being in the first video, the Z being at 180 near 180, X being near 90, and Y being 0. So we do notice some errors, so there is room for improvement. Yeah, and the second method is I had a freehand camera, or we were using the webcam to move around the object. So looking above the object, looking at the side, and then we can notice that the X and Y values are changing. Coming to the analysis of our results, real-time capturing worked really well. We were able to see the video with only just a couple frames of delay in real time. The YOLO model performed pretty well. It was very stable in recognizing the shuttle and was not sensitive to a lot of noise or other objects in the frame. The RCNN was also very fast in real time, but the issues with that was it was very, as I replaced all the classes and only the background and the object were the detectable classes, it was very sensitive to background noise or other objects or similar shaped objects. The ResNet 18 model performed really well in real time. We didn't see too much delay in the decoupling of the functionality, and our real-time results aligned pretty closely to our evaluation results with a couple of degrees of error in all the axes. And yeah, it shows great use or usability. And if we increase the number of classes, things like that, we could definitely use this in an assembly context of different parts of the shuttle. Some of our next steps include using different capture techniques, like using higher res cameras or higher FPS to see how well our model performs. Using more custom classes, like I mentioned in the previous slide, that we should probably add more parts of the shuttle to be able to detect their rotation and align with our assembly context. Definitely there's more room for model accuracy, as we did notice some degree of error in during live testing and also during our evaluation. Further fine-tuning approaches like transferred learning showed some improvement, and maybe some custom filters to help improve object detection and rotation detection could also help. Using a mixed training data of real life and synthetic could also show some improvements. And we also experimented with some depth estimation, which could also provide some more context and information in an assembly context.